All right. So lesson 16. Our lesson 16 corresponds to chapters 24 and 25 in our textbook. But our lesson 16, it's all about organic chemistry. And so organic chemistry, it's basically, if you want to think about it this way, it's the chemistry of living organisms. Okay? And so the first question we're going to deal with is this. What is organic chemistry? Or what is an organic molecule, rather? Which organic chemistry is the chemistry of organic molecules. What is an organic molecule? Now, in all three of the questions we're going to go over today, the first point is going to be your answer to those questions. So for all of these, you can just write as the answer, C first point. Okay? But an organic molecule. An organic molecule is a molecule that contains carbon, hydrogen, and sometimes other elements. Carbon, hydrogen, and sometimes other elements. That's what an organic molecule is. It's a molecule that contains carbon, hydrogen, and sometimes other elements. All right, I've got 4 molecules written on the board, and I'd like for you to write them down in your notes after you write down the sentence. An organic molecule is a molecule that contains carbon, hydrogen, and sometimes other elements. Okay, so take a look up here, get these 4 molecules written down. When I send out these notes, I'll make sure to write these molecules down. So we have this first one, CH4. Is this an organic molecule? Yes, it is, because it contains carbon and hydrogen. In this case, no other elements. What about this one? This happens to be the chemical formula for glucose, one of our most common sugars. Is this an organic molecule? Yes, it is. It contains carbon, hydrogen, and one additional element. That additional element is oxygen. Okay. What about carbon dioxide? Carbon dioxide is not an organic molecule. Why? It does not contain hydrogen. It contains only carbon. What about water? Water is not either because it does not contain carbon. So remember, organic molecules must contain carbon and hydrogen, and then can contain some other things as well. Okay, so the important thing about carbon is this. Carbon nearly always forms 4 covalent bonds. Carbon nearly always forms 4 covalent bonds. And I want to show you why this is. We've seen this before, but it was before we had our Christmas break. And so I want to show you why carbon nearly always makes 4 covalent bonds. So we've got carbon here. And if you were going to do the electron configuration for carbon, you could just look right at your periodic table and it will tell you the electron configuration. Or you can count the number of electrons and basically put them into the lowest energy level or shells first before you fill it up. But our electron configuration for carbon is 1s2, 2s2, 2p2. Okay? 1s2, 2s2, 2p2. Right? And when we're trying to figure out what an atom wants, what do we look at?
Electrons it has in its p orbital.
How many electrons it has in not just its p orbital, but in its highest energy level. So the highest energy level for carbon is what?
2.
Is 2. And how many electrons does it have in that second energy level?
4.
4. 4 total. So when we're doing the Lewis dot structure, we'll put our 2s electrons there, demonstrating they are in the same orbital, right? And then our 2p orbitals, we'll put one there and one there, demonstrating that they will stay unpaired as long as possible, right? And since all of our 2p orbitals are the same energy level, here's a 2p, here's a 2p, here's a 2p, okay? All 3 of these 2p orbitals are the same energy level. And so the electrons can stay unpaired by being in 2 different 2p orbitals, right? Okay, does that make sense? Okay, so this atom currently has 4 what we would call valence electrons. 4 electrons at its highest energy level. But how many does it want? 8. Okay? The only way to do that is to actually get 4 half-filled orbitals. So what it has to do is to actually move one of its electrons from this 2s into the 2p. And now when it does that, it has 4 half-filled p or half-filled orbitals. They're not all p. One of them's an s. 3 of them are p's. What you'll find is it actually does something. This is not exactly what happens, but it's a nice model. Is to think that what it does is it hybridizes or merges its s and p orbitals into 4 sp orbitals that are a combination of an s and a p. It's not exactly what happens, but it's sort of what happens. But anyways, now this carbon has 4 half-filled orbitals. What does it need to do in order to fill these orbitals?
Get 4 extra.
Yeah, find 4 half-filled orbitals to share electrons with, right? So we've seen this before. Do you remember doing this? And so that's what this carbon is going to do. And so because the carbon has 4 half-filled orbitals, it's going to make, bless you, 4 covalent bonds. And a covalent bond is really just, it's a fully filled orbital where 1 electron came from each atom. It's a fully filled orbital where 1 electron came from each atom involved in that bond. Okay? So we can fill these orbitals. So because carbon can make 4, which is about as many as you can make, there are some elements that will make more than 4. For instance, phosphorus can make 5, sulfur can make 6. But for the most part, 4's, that's a lot. And carbon is very stable. And so this makes carbon a wonderful element to build complex molecules out of. Wonderful. Just say wonderful. I know I said wonderful, but the slide says great. If you're like, you don't know which one to write, write both. Wonderful, comma, great element for building complex molecules. Yeah, like Dr. Engel, those 2 words mean the same thing. Why would I put a comma there and maintain both adjectives? Do whatever you want. It's your notes. Or do you not think that much when you're writing? No. You just write what you see? Yeah, I get it. So a couple more pieces about these organic molecules. One is we need to note that carbon and hydrogen have a similar affinity for electrons. And what I mean by similar is it's almost exactly the same affinity for electrons. So carbon is just as good as attracting electrons to its nucleus as hydrogen is at attracting electrons to its nucleus. Okay, so carbon and hydrogen have the same affinity for electrons. Now what this means is when a half-filled orbital from carbon combines with a half-filled orbital from hydrogen and you form a covalent bond, this bond is non-polar. They share the electrons evenly. Carbon and hydrogen are going to share those electrons evenly. Does that make sense? So does it make sense why carbon wants to make 4 covalent bonds? It has 4 half-filled orbitals, and it needs to find 4 half-filled orbitals to combine with to form a fully filled orbital. Now, since that other orbital is around a separate atom, it binds those two atoms together into a covalent bond. Okay, and if carbon does that with hydrogen, they share the electrons evenly. However, if carbon bonds to more electronegative elements, like oxygen, for example, it'll form polar bonds. So if carbon shares its half-filled orbital with the half-filled orbital of an oxygen atom, the oxygen is going to spend a lot more time with those two electrons than carbon will. They're still sharing them, but oxygen's going to spend a lot more time with those two electrons than carbon will. Is that glare bothering you on the screen? Ethan, you're probably the only one that... Can you even see the glare? Or is it just from my angle? Okay, cool. You're like, at least the screen isn't purple anymore, because that was weird. Okay. Are there any questions about this question so far? You understand what an organic molecule is? You understand why carbon wants to make 4 covalent bonds so it can get what it wants of having 8 electrons in its highest energy level, and you understand about the uneven sharing of electrons if something's better at attracting electrons to its atom than something else? Okay, good. All right, so the answer to this question, again, it's the first point. So you can write C first point, and you can do that for all 3 of our questions that we're going to... Actually, we have 4 questions. Yeah, we have 4 questions. And the last one, you actually can answer that way. You can. You can answer that way too. Sorry, I'm giving you way too much information. You're like, Dr. Engel, just wait. Let us get there. Quit ruining the surprise for us. Next question. What are the simplest organic molecules? What are the simplest organic molecules? What are the simplest organic molecules? Simplest way to answer that? Right here. Hydrocarbons are the simplest of organic molecules. Hydrocarbons are the simplest of organic molecules. What's your question at this point?
What are they?
What are they? What are hydrocarbons? Like, okay, I answered my question of what are the simplest organic molecules, but now I have another question. What on earth is a hydrocarbon? And so they are organic molecules that contain only carbon and hydrogen. They are organic molecules that contain only carbon and hydrogen. They contain only carbon and hydrogen. Now, when you hear the word simple, what do you think?
Non-complex.
Non-complex. And so that can be structurally, which is going to be true because we only have basically one type of bond. Or a couple, we've got carbon bonded to other carbons, and then we have carbon bonded to hydrogens. But they're also going to be the simplest chemically. They're going to have the least complex chemistry. But just because they're the simplest doesn't mean that there's no complexity there. For instance, these hydrocarbons, they might contain no carbon-carbon double bonds. They might contain no carbon-carbon double bonds, or no carbon-carbon triple bonds. And so we would call these alkanes. And so I want to give you an example. And so these hydrocarbons might contain no carbon-carbon double bonds, in which case they would look like this. And we call these alkanes. You see, we have a carbon-carbon bond, right? Do you see the carbon-carbon bond? There's a bond between this carbon and this carbon, but it's just a single bond. It's one orbital. Okay? One set of electrons. And one orbital has how many electrons? 2, and every bond, remember, is now a fully filled orbital where one electron was contributed by each atom. And so this represents 2 electrons being shared between these 2 carbons. Okay? And then it's a hydrocarbon. The rest of it, so carbon likes to make how many bonds? 4. This carbon is making 1 bond to this carbon, so its other 3 bonds are going to be to hydrogens. And this right here is an alkane. And specifically, it's an alkane with this formula, C2H what? 6. See, that's as complex as the math gets in this section, counting the number of each type of element. It's wonderful after finishing a discussion on acids and bases, right? To just be like, okay, I can count. Okay, so here is an alkane. No carbon-carbon double bonds. Now, your hydrocarbon might contain at least 1 carbon-carbon double bond. It might contain at least 1 carbon-carbon double bond. In which case we call it an alkene. Okay, contain at least 1, or you could say contains 1 or more carbon-carbon double bonds. At which point we would call it an alkene. And so let me draw one of these for you. We still have a molecule that contains 2 carbons, although now we have a carbon-carbon double bond. Do you see that on the board? You see our carbon-carbon double bond? So each of these is a fully filled orbital where 1 of the electrons was contributed by each of the 2 carbon atoms. But they are sharing 2 orbitals, or 4 total electrons. Does that make sense? Josh?
So would it have 5 hydrogens then?
Oh, we'll see. Let's count them. So this carbon is making how many bonds? 2. How many does it want to make total? 4. So 2 more. And those are going to be to hydrogens, because this is a hydrocarbon. This carbon is making how many bonds? 2. So it's going to make how many more? Also 2 more that are each going to be to hydrogens. Okay? So the formula for this hydrocarbon, which is now an alkene, is C2H what? H4. And it is now an alkene, it is not an alkane.
It's so nice of them to name them that way.
Is it?
It's so nice of them to name them that way for all the students.
Wait till you see the next one. You're gonna like this. It might contain at least 1 carbon-carbon triple bond, at which point we would call it an alkyne. Still moving in alphabetic order. Alkane, A comes first, that's only single bonds. Alkene, only single and double bonds. Alkyne, single, double, and triple bonds, or at least a triple bond. Alkynes might contain at least 1 carbon-carbon triple bond. Alkynes. Okay, so I've drawn one on the board for you, an alkyne, at least the beginnings of an alkyne. We have 2 carbon atoms with a triple bond connecting them. Each bond represents a filled orbital with 2 electrons. So these carbons are sharing how many electrons? 6. Okay, they're sharing 3 orbitals, 6 electrons. How many bonds is this carbon making right here? 3. How many more does it need?
1.
1. And it's going to be to hydrogen because this is a hydrocarbon. How many bonds is this carbon making? 3. So it needs to make how many more? 1, and it's going to be to hydrogen, and the formula for this is C2H2, and this is an alkyne. So why doesn't our alkyne have as many electrons as our alkane and alkene do?
Less molecules. or less?
Yeah, I mean the carbons are sharing more electrons among themselves. So there are less electrons to share with a hydrogen atom that has a half-filled orbital. Okay? And so we call alkanes saturated. They're saturated with hydrogen. They have as much hydrogen as they can possibly hold with the amount of carbon they have. These alkenes and alkynes, these are unsaturated. Joe?
Is it possible to have a quadruple bond?
A carbon-carbon quadruple bond is theoretically possible, but it doesn't happen.
Yeah.
It's theoretically possible, but it doesn't happen. Because when you have only carbons, you form something like graphite or diamond or coal, something like that, and then it behaves more like a metallic bond, where the electrons are kind of just pulled among all the atoms. So yeah, it's theoretically possible, but it doesn't happen. Yeah, it's a good question. And why it doesn't happen is complicated. And so, we can get into some quantum mechanics if you want, but you could just suffice it to say it's possible, but it doesn't happen. Okay, and so have you heard the terms saturated and unsaturated used for fats? So a saturated fat only has these types of hydrocarbons in them. They're saturated. They have as many hydrogens as you can pack for that amount of carbon. Unsaturated fats tend to have double bonds and very occasionally some triple bonds in them as well. So they are unsaturated. They do not have as many hydrogens as you can possibly pack into them. All right? One more thing we need to talk about are hydrocarbons. They might form a ring, and we call these aromatic hydrocarbons. Yeah, of course. And so they might form an aromatic hydrocarbon, and they might form a ring. Now I can't do a ring with just 2 carbons. So the smallest ring that you're going to find contains 3 carbons. So here is a wonderful example of an aromatic hydrocarbon. An aromatic hydrocarbon. Do you see the ring? And the ring doesn't have to be a circle, it just means that they're all basically attached in sequence. Okay? And they're not aligned. You basically can just keep going around and around and around and never run out of carbons. Now, how many bonds is this carbon making right here? 2. So how many more does it need to make? 2. And it's going to be the hydrogen because it's a hydrocarbon. What about this carbon? 2, and it needs 2 more. What about this carbon? 2, and it needs 2 more. And so the formula for this hydrocarbon would be C3H6. Now notice here with our alkane, we were able to pack 6 hydrogen atoms on only 2 carbon. Yes? Over here it took us 3 carbons to get 6 hydrogens. So even aromatic hydrocarbons are unsaturated. They don't have as many hydrogens as you can pack in for that amount of carbon. Okay? Does this make sense? Alright, so what are the simplest organic molecules? Again, for this one you can write C first point, but there are a couple of terms I want you to look up. One is hydrocarbon, and the other one is aromatic hydrocarbon. I want you to look up hydrocarbon and look up aromatic hydrocarbon. Okay, any questions about this question? All right. So what are more complex organic molecules? What are more complex organic molecules? Oh, you know what?
Actually, I found it. Thanks.
Oh, you found it?
Yeah,
Okay.
thank you.
So what are more complex organic molecules? More complex molecules contain at least one functional group. More complex organic molecules contain at least one functional group. more complex organic molecules contain at least one functional group. What's your question at this point?
What is
What's a functional group? Like Dr. Engel, you're getting into the habit of answering questions in such a way that all it does is provide additional questions. And you're right, but it's for your edification. And so I am going to give you 6 functional groups that are the most common functional groups to find in organic molecules. Now these are no longer hydrocarbons because these are going to now contain elements in addition to just carbon and hydrogen. Okay? The first example, a hydroxyl group. First example, a hydroxyl group. A hydroxyl group. And so I'm going to draw all of these functional groups for you. They show you what the elements are and their, approximate configuration. But I'm gonna show you these in more detail. I'm gonna draw them out for you. So the first functional group is called a hydroxyl group. And in a hydroxyl group, you have one of your carbons is bonded to an oxygen that's bonded to a hydrogen. So one of your carbons is bonded to an oxygen that is bonded to a hydrogen.
Sorry.
You're fine. And so, right now, how many bonds is this carbon making? 2. How many bonds does it want to make? 4. And so the other 2 will just be hydrogens, because we haven't noted the presence of any other functional groups. What about this carbon?
1.
It's making 1 bond. How many more does it need? 3. And they will all be hydrogens. And so now this is an organic molecule that has a hydroxyl functional group. And this, in case you're curious, you don't need to know this, but in case you're curious, we would call this molecule ethanol. Ethanol. Or ethyl alcohol. The next functional group, a carbonyl group. A carbonyl group. And so now we've got a CO. I'll draw this one for you as well. Wow. Thank you, and I'm sorry. Okay, so a carbonyl group. One of our carbons has a carbon-oxygen double bond. One of our carbons has a carbon-oxygen double bond in this carbonyl group. Now, how many bonds is this carbon making right here? 3. How many more does it need? 1. And that's going to be to a hydrogen because we haven't noted the presence of any other functional groups. And this carbon, how many bonds is it making? 1. How many more does it need to make? 3. And they are all going to be hydrogens because we have not noted the presence of any other functional group.
So, when you say we have not noted the presence, is that because it says they contain at least, no, it says at least 20.
Well, because I would tell you if they had more than just this functional group.
Okay.
But I'm drawing basically as simple of a molecule as I can with these functional groups. Although I could have actually drawn one for this one that only had 1 carbon. Yeah, so this isn't as simple as I possibly can. I could have drawn this simpler, but I didn't. Yeah, Ethan.
Are all hydroxyl molecules
Alcohols?
bases? Yeah.
Are they all bases?
Yeah.
Bases? They will behave sometimes they'll behave as an acid or a base, depending on what the solution is. Remember, there'll only be a base if they donate that OH as a unit. And so they can have OH and not be able to donate it. But a lot of alcohols can under certain conditions. Yeah. They'll usually only donate it if the solution's really acidic. So when exposed to an acid, they'll sometimes act as a base. But yeah, that's a good question. And they're all alcohols. Anything with a hydroxyl group is an alcohol. So you have methyl alcohol or methanol, ethyl alcohol or ethanol, propyl alcohol or propanol. Isopropyl alcohol, if you use that, you have that in your house. No? Maybe. Okay. So here, this right here is ethylaldehyde. Okay, in case you're curious what these are called. Then we've got a carboxyl group. A carboxyl group. COOH. And so in a carboxyl group, one of our carbons is double bonded to an oxygen and then singly bonded to another one that's bonded to a hydrogen. So in our carboxyl group, we have one of our carbons is double bonded to an oxygen and then singly bonded to another one that's bonded to a hydrogen. Okay? How many bonds does this carbon on the right form?
3.
And it's got 4.
4 actually.
Yeah, because it's got 2 bonds with that oxygen, so it's already satisfied. It's already got 8 electrons. Okay, what about this carbon?
So yeah,
Just 1, so it needs 3 more that are all going to be hydrogens. Unless I told you we were going to represent another functional group, which we are not. And so this, in case you're curious, this is called ethanoic acid. Ethanoic acid. And you're like, wait, acid, I know that. I know that acids dissociate from hydrogen ions. Which hydrogen ion do you think would dissociate from this molecule?
That one.
This one over here. Because these carbons and hydrogens, they're sharing electrons evenly. That's a very stable bond. This oxygen, we know it's an electron hog. These are not sharing the electrons very easily, and this hydrogen is the one that dissociates. And so with it, it's called ethanoic acid. If it does not have it, it's called ethanate. But anyways, that's just bonus information. You don't need to know those names. I just want to share them with you because they're written on the board, and some people like to know that. The next one, an amino group. An amino group. An amino group. So one of our carbons is bonded to a nitrogen that's bonded to 2 hydrogens. One of our carbons is bonded to a nitrogen that's bonded to 2 hydrogens. How many bonds is this carbon making? 2. How many more does it need?
2 more.
2 more that are each hydrogens. This one making how many bonds?
1.
1, so it needs 3 more that are each hydrogens. And in case you are curious, this is called ethylamine. 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 You're like, that's kind of a fun name to say. Or maybe you're like, wow, that's a terrible name to say. All right, 2 more. The next one is a phosphate functional group. A phosphate functional group. And so here, one of our carbons is bonded to an oxygen that's bonded to a phosphorus that's bonded to 3 other oxygens. That's a big functional group. That's a big, bulky. This carbon is making how many bonds? 2, so it needs 2 more. This carbon is making how many bonds? 1, so it needs 3 more. And this would either be called ethyl phosphate or 1-phosphoethane. Yeah.
Do the other 3 oxygens only have 1 bond?
That is an excellent question. They actually all have 1 and 1/3 bonds, but that's getting into some complex chemistry that you don't need to know yet. Yeah. So suffice it to say at this point, yes. Each of these additional oxygens only have 1 bond with that phosphorus. But yeah, phosphorus can make more than 4 bonds. It was one of the examples I gave you earlier. It can make up to 5 bonds. And so anyways, what you get is basically 1 1/3 bonds with each of those oxygen. Like, how does it make sense? How can you have a third of a bond? It's like, at one specific instant, the double bond's here. At the next instant, the double bond's here. The next instant, the double bond's here. Then it's here, then it's here, then it's here. So at any average state, there's 1 1/3 bonds with each oxygen.
So the electron is kind of going from the O
Yes.
to the P to the other O to the P.
Yeah, but it's not, it's, yes. But it's complicated. Yeah, because, yes, yeah. It's more complicated chemistry than what you need to know.
Why does phosphorus make more than just 3 bonds?
Or more than just 4.
Well, yeah.
Because it violates the octet rule. It's most satisfied when it has more than 8 electrons in its outer shell. And it has a lot to do with the fact that it's bigger. Its p orbitals are larger, and they can hybridize with s orbitals and with d orbitals. And so it gets a little weird. When you start getting really big atoms, some weird, strange things can happen. Yeah. And then the last one, sulfhydryl group. Sulfhydryl group. Oh, we're doing well. And in our sulfhydryl group, one of our carbons is bonded to a sulfur that's bonded to 2 hydrogens. Okay, how many bonds is this carbon making right now? 2, so it needs 2 more. And this carbon? 1, so it needs 3 more. And the name of this would be 1-sulfhydryl ethane.
It's getting weirder and weirder and
It is getting a little weird. And so that's why you don't need to know how to name these complex organic molecules yet, unless you go and you study chemistry or biology at the university level, at which point you'll take organic chemistry and you will name lots of organic molecules. Ethan.
Why does sulfur make 3 bonds? Is it the same way like phosphorus?
Well, a sulfur can actually make up to 6.
Okay,
And
it's
so,
also-
yeah, in this one, sometimes it'll make a single bond with that carbon, other times it'll make a double bond with that carbon. And yeah, it's different. It's different. Yeah, sulfur and phosphorus, they do some strange things. They don't satisfy the octet rule often. Now, oftentimes what you'll find is there'll be a double bond between that carbon and the sulfur, and then the sulfur will have its 8 bonds, and that carbon will have 1 less hydrogen bonded to it. So you can find that. So what are more complex organic molecules? Again, answer this by just saying see first point. I don't have any key terms I need you to define in this point, but do you have any questions? It's basically just a matter of identifying functional groups. So you'll have some questions on your homework worksheet where it'll ask you to identify some of these functional groups. Yeah, Josh.
So if S can make 6, that would
This S will not be able to make
It will-
6.
okay, because like it's not gonna be satisfied then, really, because it would need to make 4
You're-
bonds with C, which is
You're right, it is very dissatisfied and it is very highly reactive. It's a very reactive functional group. You are exactly right. It is very dissatisfied. And it's very chemically active.
The last one?
Yeah, that last one. Yeah. And so, do any of you have wavy or curly hair? You've got wavy hair. And so with wavy or curly hair, what's happening is in your proteins that make up your hairs, these groups, these sulfhydryl groups from one amino acid will actually form bonds with a sulfhydryl group from another amino acid, curling your hair fibers. And so you can chemically straighten your hair by breaking these bonds, or you can break them with heat. And so you can straighten your hair with heat. You know, you've seen that happen, yes? People straightening their hair with heat, and so you can break those bonds. But it is very reactive. It's a very reactive function group. Any other questions on this question? All right. So how do we name organic molecules? Now, there's nothing in your homework that is going to ask you to name organic molecules, but I want to give you some tools so that if you go on and you take some additional chemistry, You basically already have a foundation to build on for this. Okay, and here's how we name them. First thing we do is we name the parent hydrocarbon. We name the parent hydrocarbon. We name the parent hydrocarbon. And here, in order to do this, we need to count the number of carbons. We need to count the number of carbons because that's what's going to determine the name. You ready to do this? If it has one carbon, the parent hydrocarbon is methane. So if the parent hydrocarbon has one carbon, it is called methane. If it has two, it is called ethane. If it has two carbons, it is called ethane.
Is that why they're all called ethanol?
Ethanol, ethanoic acid, ethylaldehyde, ethyl phosphate, ethylamine. Yep, because we've named the parent hydrocarbon. That's ethane. Now, when would you not expect to call it ethane? Because A and E ends in the same ending as alkane, right? What if it's an alkene? What if it has a carbon-carbon double bond? Then we don't call it ethane, we call it ethene. What if it has a carbon-carbon triple bond? We call it ethyne. Okay, and so if it has three carbons, this parent hydrocarbon is propane, or propene, or propyne.
If you get propane gas, is that literally just three carbon atoms carbon molecules connected?
If with nothing else on it? What was your question?
And it's just plain propane gas, is that just three carbon?
With the hydrogens. Yep. Now propane gas that you have in your grill or in a big tank to heat your house with, it's mostly cyclopropane. That one I drew up on the board where it was a triangle. But it can be just regular propane. That's not in an aromatic ring. If it has four, it's butane, or butene, or butyne. Butane, butene, butyne. If it has five, it's pentane, or pentene, or pentyne. Pentane, pentene, pentyne. What if it has six? What do you think? Hexane. Hexane, hexene, hexine. Hexene, hexane, hexene, hexine. If it's got at least one double bond, it's hexene. If it's got at least one triple bond, it's hexine. If it doesn't have either, it is hexane. What about seven? Or in this case, we use the heptane, heptane, heptene, heptyne. Now, Dr. Engel, how many are we going to go through these? We're only going up to 40. So, it'll be fine. There we go. I made that same joke on Monday. We're not doing 40. We're only doing 10. Number 8, octane. Octane, octene, octine. Octane, octene, octine. You seen at a gas station, they give you the octane rating? It's a measurement of how much of the hydrocarbon in that gasoline is octane. The higher the octane rating, the cleaner it burns.
No, like a person in a game that goes really fast and their name is Octane.
Octane? Yeah. Yeah, I mean, higher performance cars need gasoline that's going to burn a little bit cleaner. So it's not that octane is better. like produces more energy. It just burns a little cleaner. Burns a little cleaner than some of our other hydrocarbons. 9, nonane. Nonane, nonene, nonine. Nonane, nonene, nonine. And then finally 10, decane, decene, decine. Decane, decene, decine. If your parent hydrocarbon has 10 carbons. All right? So that's the first thing we do. First we name the parent hydrocarbon, then we note any extras, like any functional groups that are added on, or if there are possible isomers, we'll name which specific isomer that we have. So sometimes we can produce two different versions of the same molecule that are mirror images of each other. We call those enantiomers. Two different versions of the molecule that are mirror images of each other. That is, one of them rotates to the right, one of them rotates to the left. We call those enantiomers. And then sometimes we just have other structural isomers. And so I want to real quick give you an example of the structural isomer that we've already seen so far. You don't need to write this down, I just want you to appreciate the structural isomer. Okay? Here's our formula, C3H6. Alright? C3H6, you see that? So here's our formula. This could look like this. Okay? This could look like this. Do you see how that is C3H6? And what would we call this?
Propane.
Propene. It'd be propane if there weren't any double bonds, but since there's at least one, it is propene. Okay? So that's one structural isomer, and then one we've already drawn before. That would also be C3H6, right? Do you agree? So these are structural isomers of each other. Same formula, very different shapes. Right? Same formula, very different shapes. Are they mirror images? Are these two mirror images of each other? Nope, so they are not enantiomers, they're just structural isomers. Okay? And so that's why sometimes we have to call this cyclohexane or cyclopropane so that we know what we're actually talking about. Okay? But that's it. And that's something to do that goes beyond what your homework will ask you to do. And so now you can, talk to all your friends and be like, hey, you know what propane really looks like? Because I do. And then you can show them, they'll be very impressed. They'll respect you. Probably value your friendship more. All right? Have a wonderful day. I'll send out these slides tomorrow or Friday. And I'll make sure I put the drawings that I did on the board onto the slides so you can see an extra copy of them in addition.